Well, as soon as you start rotating, you do get a net helicity, but of course it's small. So what you really want to calculate is the relative helicity. And so this is what it is. This is like u dot omega over u squared omega squared. So
it's a continuous function of the rotation.
I would think so, yeah.
And that happens with and shear flow. Does that happen with both? With the shear flow and without shear flow?
Well, we add in a shear flow to something that already has something with net helicity. And then the shear probably has some helicity of its own.
Right, so the net helicity you are computing is from the fluctuation.
This is from the interaction of the fluctuations with the rotation and the penetration.
But you can have a generation of net helicity without shear flow.
Just a large scale shear flow. Yes. Sorry.
Mike, just listening about the influence of rotation on penetration, there must be
There
a
is.
size of Taylor number. You just didn't look in that review.
For large enough Taylor number, I'm sure it has to affect the
the
penetration
joining.
because that's right. You don't get very large vertical flows compared with horizontal flows. So there must be, but this is not a strongly rotating regime.
No, I understand.
But for the ones we looked at, it's very weak.
I mean, the Taylor numbers you're using, I thought about the numbers. They're appropriate.
Who
knows?
Rossby numbers about 1, I think. So.
Okay.
It's not for strongly rotating now.
Is there another question before Nathan? Did you have one? Yeah.
This is about the slide you had shown earlier, magnetic peak. Where is the viscous cutoff?
Okay, so this is a magnetic Prandtl number 5. So the viscous cutoff is to the left of the magnetic cutoff. Yeah. Which is why I say you should really, if everyone's interested in the high magnetic Reynolds number problem, you should really just forget about the spectrum in the velocity and just put a flow of one scale there. And then, because you're interested in everything that happens to the right. But yeah.
Okay, last question.
What is the typical size of your turbulent eddies comparison with depth of your convective zone?
For what rotation? I mean, rotation affects these things strongly.
No,
For non-rotating. Yeah, it's about the depth.
About the depth. So my question is, what's the origin of this high helicity? It's a really high helicity. I mean,
well, that's for rotating.
No rotating case. At least it's a little bit surprised that you find it. But only all theories should be zero. Maybe
no, because we've broken the up-down symmetry.
Yes,
it's the penetration. So the flow is not symmetric about the z is equal to 0.5.
Right.
So you by hand introduce helicity in the system?
No, you just rotate and it's helicity.
But rotation equals zero in this situation.
And it has zero helicity. Zero helicity. And then as you
I
start to
see.
rotate it,
I see.
sorry,
Yes,
maybe it's badly labelled. You get something.
Yes, it's my fault. I'm sorry. Okay, it's okay.
Okay, we'll then move on because we're already running late. Let's thank Steve again.
Basically zero.
Next. Okay. Okay, our next speaker is Becky Young-Heeman with an intriguing title, The Electric Sail, a New Vehicle in the Solar System.
Okay, thank you. Do you hear me?
Yeah.
Yes, good. Okay, so this talk is about, is a quite different topic, than the rest in this conference, but I think it's anyway of interest for you to hear about it, and also at the end you will find that there is some connection to the workshop topic anyway in this thing. So here is first of all my list of collaborators, so you can see if you find some familiar names there.
You have to leave it up for a while then.
Yeah. Okay. So the contents of this presentation is, the topic is the electric sail. So what is electric sail? So it means that we use the solar wind dynamic pressure for pushing a spacecraft, for spacecraft propulsion. And it has some similarities with the ordinary solar sail, solar photon sail, and also the ordinary ion thruster or electric propulsion. So we kind of describe the present status of the thing, and then the one potential application in a little bit more detail, which is the so-called IHP, means Interstellar Heliopause probe, and then also other space mission applications. So some kind of brief history of solar wind propulsion. To my knowledge, the first idea of solar wind propulsion was proposed by Robert Zabrin and Dana Andrews in the late 1980s or so, using a so-called magnetic sail. So the idea there is that one deploys, one installs a large dipole magnet in a spacecraft, and then one obtains a large, a modest-sized magnetosphere, artificial magnetosphere around the spacecraft, and then the ram pressure of the solar wind pushes this magnetic bubble in the solar wind. So the thrust that one obtains is roughly the solar wind dynamic pressure multiplied by the cross-sectional area of this artificial magnetosphere. We studied this actually in our group about 4 or 5 years ago for ESA, and it was found that it's presently unfortunately not feasible to implement due to some technical limitations and also some guiding issues. However, this idea that since the solar wind exists and it's kind of everywhere, then the idea was kind of lived on that would there be some other way of using the solar wind dynamic pressure for spacecraft propulsion, and then it's rather logical kind of that if the magnetic field doesn't work, then what if the electric field then does work? And then this was considered and it seemed to work initially, and then this was published in 2004 at an idea level, and then a technical implementation plan came 2 years later, and then after that this has been kind of rapidly progressing as it has been kind of gradually realized that this is really also not only in theory but also in practice a viable method of achieving high speeds for spacecraft. So the working principle of this electric sail is the following. So we deploy thin and long positively charged tethers from the spacecraft which form an obstacle for solar wind protons in such a way that there is a momentum transfer taking place from the solar wind protons to the tethers. And the tethers have to be kept artificially in this high positive potential. We do it by an onboard electron gun which is solar powered, and then these tethers have to be stretched kept in a stretched configuration in some manner. So we propose to use simply the centrifugal force for that purpose. We are spinning the spacecraft and keeping the tethers taut in that way. And then also it's very important that in order to be a viable method for space propulsion, we also have to have a method of guiding this thing. So then we use the following fact that the thrust on each tether depends on its voltage, and this voltage can be tuned individually for each tether by having a potentiometer between the tether and each tether and the spacecraft. And then one can use a helicopter flight-like algorithm for turning the spin plane, where in the helicopter case the attack angle is analogous to the potential of the tethers in our case. So the main features of this, the kind of technical features of this propulsion method is that it's relatively simple and kind of scalable architecture. It has a set of small and identical reels. Can be any number of them in principle at least. It has high performance, and this high performance comes from the fact that the kind of electric width of these tethers or wires is about 1 million times larger than the physical width. So the electric width is of the order of the plasma Debye length. In the solar wind is about 20 meters, and the physical width we can make it as thin as 20 microns. So there is the factor of million there. So the surface area of the sail is kind of 1 million times larger than the physical area, and that gives us the high performance. And then there is this natural way of guiding it, so we can do some thrust vectoring, which is important, and we can also do electric throttling, which means that we can turn off the propulsion very simply by just turning off the electron gun. And also the fourth benefit of this is that the thrust decreases slowly with the radial distance from the sun. So in this electric sail it goes roughly like inverse of the radial distance, while in the solar sail and solar powered ion engine it goes like 1/2 distance squared. So this is the geometric configuration we are proposing to use. Here is the spacecraft at the center, here is the solar wind coming, and these tethers are deployed like this, and then the electrons are shot out of the spacecraft. So that doesn't work, okay. But we can take this animation from in this way. So in the initial state we have the spacecraft here, then we set it to spin. These blue things are just solar panels. Then we start to deploy the tethers. We just unreel the tethers from their reels. In this case we show only 8 of them, but in reality there is more. There are some small rockets in this case on the tip of these propulsive arms, which kind of increase the angular momentum of the system during the deployment, so that the spin doesn't slow down although one deploys the tethers. So eventually this deployment is complete, and then we have this kind of ready flying package. Then we can throw out this auxiliary spin-up propulsion system to save weight. And then the solar wind exists there, but it doesn't do anything until we turn on the electron gun now. So then after that, this electric sail effect starts. So this effective area of these tethers grows to this 50 meters or so. And then the solar wind is actually also, it's variable, of course, as you know. So which means that our tethers start to oscillate to some extent, but it's not really a problem. One just has to be aware of it. So that's the principle, really.
Where's the electron gun shooting at?
It was this blue line here. That was the electron beam, basically. But in principle, it can shoot in any direction. So the direction doesn't matter. The only thing is that it has to get the electrons out of the potential of the spacecraft. So it can equally well shoot also upstream or downstream or both. Or
okay, just remove charge from the
yes. The electrons are so lightweight that the momentum flux that they carry is completely negligible. We don't have to worry about that.
you can shoot protons backwards.
Yes, but Okay, then some physical parameters. So the solar wind dynamic pressure at 1 AU distance is about 2 nanopascals. I mean, that means density times velocity speed squared. And then the electric radius of the tether is about the Debye length in the solar wind, which is about 20 meters. Or actually the Debye length itself is about 10 meters, but its electric width is somewhat larger, so there is some numerical factor in front of it. So yes, and of course, I mean, this Debye length scales with the square root of the solar wind density, and also the inverse square root of the solar wind density, and also as the square root of the solar wind temperature. So it's not constant, but this is the average value at 1 AU distance. And in a full-scale mission, we would typically use 50 to 100 tethers of 20 kilometer length each, and the diameter of the wire would be 20 microns. And with these setups, we get a thrust which is something like 0.1 or 0.2 newtons. And in a typical, if it's a small spacecraft, then we can expect to have an acceleration which is a few millimeters per second squared. And then the electron current that the tethers are gathering from the plasma, it can be easily computed from this cylindrical Langmuir probe theory. It's few tens of milliamperes typically, or let's say that the maximum is about 50 that one can get from the solar, what one can get from the solar wind. And the typical voltage is about 20 kilovolts that we would use, and then the force per unit length of tether would be something like between 50 and 100 nanonewtons per meter. So from this one can kind of scale that how much tether one has totally, and then one gets this total force. And the point is, I mean, the why this is feasible is really it's crucial that this electron current is really quite small, or not small, but let's say modest. So the power in the electron gun that you need is not flux. It's only a few hundred watts basically. So you can easily get it from modest-sized solar panels. Okay, and then something about this simulation. I mean, this idea has that the plasma physics works. It has been kind of verified in a particle-in-cell simulation. I mean, where we calculate really the orbits of individual electrons and ions self-consistently. So it's a two-dimensional calculation. We put a charged wire at the middle of the simulation box in a solar wind, and the relevant length scale is the Debye length of electrons, as I said. And this, on the surface, this looks kind of simple simulation to do, but actually, when one looks at the details, it's quite challenging to reach an accurate result. One reason is that we want to use, or we have to use, a realistic electron-to-proton mass ratio, which makes our time step rather small, and also then the electron temperature of the solar wind is much. It's about 10 electron volts typically. It's much smaller than the voltage of the wire, which is about 20 kilovolts. And another reason for this kind of challenging nature of this problem is that because it's a two-dimensional problem, then the vacuum potential of the wire has a logarithmic dependence on the radial coordinate, which kind of introduces a scale-free aspect of the problem. So it's a multi-scale thing, basically. Intrinsically, you have to calculate. So you need rather large grid. So anyway, after doing this calculation by kind of brute force method, simply, then we determine the force by two complementary methods from the simulation. One is that we just use Coulomb's law. F is Q times E at wire, so Q is the charge of the wire and E is the electric field caused by the asymmetrical proton and electron distribution around the wire. And then also we computed this force by a particle momentum budget. So we, at all boundaries of the simulation box, one keeps track of the momentum, incoming and outgoing momentum, when each particle crosses the simulation box boundary. And as often in numerical simulations, the results computed at such widely different methods, they differ to some extent, which gives anyway to us some kind of error estimate. So analytically they should be equal, of course, but the numerics, they are not completely equal. But still, the result is kind of accurate enough to be useful. So here is an example of the simulation result. So the solar wind is coming from the left, and the wires is sitting somewhere here, and this is kind of it's really like a magnetosphere. Looks like a magnetosphere. We should perhaps call it an electrosphere or something like that. So this is the proton density. So the protons are accumulating here because they are repelled by the positive charge of the wire. And this region is completely void of protons, but of course there are electrons in this region. And then so we calculate the force per unit length, and then the thrust on the spacecraft, and then we can calculate the trajectory of the spacecraft if we pick up some concrete mission. And in this case we have calculated the flight out of the solar system using some kind of as realistic parameters as possible. So then the speed kind of increases rather well in the beginning, and then it kind of levels off. The acceleration goes like 1 over radial distance from the sun, so therefore it kind of asymptotically approaches some value which is more than 40 kilometers per second in this case. And here is the corresponding radial distance. So after 3 years, for example, we are at 23 AU distance. And this is Pluto distance about 30 is crossed earlier than 4 years in this case. Okay, I think I skipped this one. This is just a kind of hardware list, so I mean, but more technical. This is also, I also skipped this one. Okay, I just say that, I mean, this, for micrometeor tolerance, these tethers cannot be single monofilament wire, but they have to be made in a multi-line way like this. So this is called the Hoyt-tether approach. So that the idea is that if and when micrometeors break these individual wires randomly, the probability that this structure is broken as a whole is quite small, because it would require that one has kind of 4 breakings of these wires at the same near each other, and one can calculate the probability, and it's very, very low. So the lifetime of this tether is very long in space when using this. I mean, the micrometeor flux at this scale size is rather well known. So yeah. Okay, so this was now the baseline approach, but there are some ways to increase thrust. So perhaps so one of them, I mean that an important, I mean that the main thing what we are considering is to do some radio frequency heating of the trapped electron cloud, because that would increase basically the effective Debye length of this electron, of this trapped electron population, because the Debye length is proportional to the square root of the electron temperature. So if you heat the electrons, then you get this cloud becomes wider, and then you get larger effective surface area for the sail, electric sail. So this is kind of hard to model, but for various reasons into which I don't go to now. But it would be easy to test experimentally in space, and this is one reason why we are thinking that one should, as soon as possible, makes a small test mission of this, because it would give us not only verify that this concept works as a whole, but also give us quantitative information concerning this thrust with and without radio frequency heating. Okay, so then there are some, I would say, issues. I mean, of course, every technology has some kind of list of issues. So this is ours. Perhaps I don't go into these details now, but I mean, you can see that. Okay, very shortly. So micrometeor cuts, they are under control. Then this some mechanical things related to reeling of the tether, but it can be. I mean, there are kind of at least two ways to resolve this, and at least one of them works. So certainly works. So. And then the stochastic nature of the solar wind, but it's not really a problem. At least not a problem in this high HP mission, where one just wants to fly out of the solar system. There this accurate navigation is not critical. And also this one last thing is that we are not sure if we can allow users of this technique to fly through the eclipse of planets or moons, because of thermal expansion of the wires and then possible oscillations caused by that. So, but in many missions such as IXP, this is not a problem. Okay, here is some ongoing work. So tethers are kind of being, I mean, the tether manufacturer is being looked at University of Helsinki, and then DLR Bremen, they kind of started to look at it in this real development. Electron gun design has been made in Moscow Space Research Institute, and then orbital calculations have been made at the University of Pisa, and then some kind of mechanical flight simulator has been programmed in a company in Finland. And then this tether, we need also kind of tether direction sensor here. So for guiding the spacecraft, we need to know the instantaneous orientation of each tether during flight. So that's sensor is now start developing it in Uppsala, Sweden, Ångström Space Technology Center. Okay, then one of the applications is this potential applications is this interstellar heliopause probe. So what is the IHP? So that's scientific objectives are threefold basically. So the primary one is first in situ measurement of interstellar medium. That means gas, plasma, dust, magnetic field, and cosmic rays outside the heliosphere. And then secondary objective is of overall study of the heliosphere and heliopause region and its turbulence and so on. And then a third, like a bonus, scientific bonus, is the Pioneer anomaly test, which is fundamental physics question, which requires that one flies kind of far away. And then the requirements, more specifically, one should reach 200 AU distance in less than 25 years, and this means that the speed must be larger than 40 kilometers per second. And in the baseline approach, the instrument payload is 25 kilograms with 10 instruments. And this has been, ESA has studied this earlier using different, these classical propulsion systems, including solar and nuclear electric propulsion, and also chemical rockets and solar sail. So the solar sail is kind of, it would work if one can build a very large one, but it should be as large as 250 meters. So it's, they considered it to be too difficult to do technically. So that's why the first iteration, at first iteration, this IHP proposal, which was submitted to ESA, was rejected because of this technology issue related to the solar sail, which was at that time considered as the primary option. So really this is the solar sail proposal, which was already made and rejected, specifications of it. So we could also do this with, we think that we could do this with electric sail, and one feature, we would probably do it in such manner that we divide the payload into two spacecraft. So we would have two spacecraft which would be launched at once and separated in space and actually spun in opposite directions, actually to get the spin up for them, and then they would fly independently. And this would bring some bonuses also, that scientific bonuses, that it would give a 2-point measurement of the solar heliopause region turbulence, and also the Pioneer anomaly study would benefit actually from having two independent measurement points.
May I ask something about the Pioneer anomaly? Since if you want to detect it, you have to be sure that you know all phase forces.
Yes, certainly. That's,
so
that's yes. Okay, so
training is a bad idea.
yes. So we would do so that we would set this on this electric sail at for example, Uranus distance.
Okay, switch it off.
We'll switch it off completely. So that would be also done in the solar sail case. So, yeah, exactly. And then some other applications. So for this electric sail, so one application would be off Lagrange point solar wind monitoring. That means that we are kind of hanging between Earth and Sun against solar gravity to some extent to monitor solar wind and forecast space weather with a warning time which is larger than 1 hour, or longer than 1 hour. 1 hour is the time that the traditional Lagrange point solar wind monitoring gives to us. The travel time of the solar wind from the Lagrange point to Earth is 1 hour, but now we would place the spacecraft closer to the Sun wherever we want and have a longer warning time. And then the mission visiting multiple asteroids is kind of an obvious thing to try here, because we don't use any fuel, so we don't run. Our delta V is not limited. It's only limited by the physical braking of the device. And then one thing that has been a little bit considered is would be a Jupiter Lagrange point probe, which would simultaneously measure the solar wind hitting Jupiter's magnetosphere and also image Jupiter's aurora at the same time to get the find the auroral response of Jupiter to the solar wind really. And then some one could have, I mean, concerning the outer solar system, I mean, with this technology, it's kind of easy to make a flyby probe, but it's not possible to stop there. So of course, because if we are flying at high speed, I mean, there is no way we can stop. But we can make a flyby. And it's relatively cheap because the mass is low. So we could even have a set of such small probes, each targeting different distant objects in the solar system, Kuiper belt and so-called Centaur objects in the outer solar system, to make a flyby of each and make those measurements that one can from this flyby. Okay, and then the validation part is like this, that we first would like to have a test mission, a low-cost test mission at high elliptic orbit, Earth orbit, deploy only 8 tethers of 1 kilometer length each, small spacecraft, and the objective would be to measure the thrust by an accelerometer, but the thrust would be so deliberately made so small that it wouldn't change really the trajectory of the spacecraft. This would simplify this mission design also. And then at the same time we would certainly test electron heating. I mean that the objective here would really be verify that the principle works and measure quantitatively the thrust in different solar wind conditions and different voltages and different radio frequency heating rates. And then the second test mission would be one with longer tethers, and then we would really use it for a propulsive purpose and pick some target, for example an asteroid, and then also demonstrate this flight trick, so to say. This is spin plane thrust vectoring, and the cost would of course be clearly higher here without instruments. Long-term commercial application. This is a really long-term. So I mean, but the idea here is that since this electric sail, I mean, it gives you a high mass multiplication, high payload fraction, basically. So one could kind of ferry some stuff from asteroids to Earth orbit using this electric sail in an economical fashion, in an economical way, because this spacecraft, which the electric sail package is lightweight, weighs only about 70 kilograms perhaps, and then it could bring even some tons of material at one flight. So one could have a cluster, I mean several of these small spacecraft like this, and they would each get a payload and then form this kind of logistic chain to fetch especially water, for example water from asteroids. I mean, water is kind of important because once decomposed into hydrogen and oxygen, it is rocket fuel. So one could manufacture rocket fuel on orbit, and thereby one could cheapen these satellite launches to geostationary orbit and elsewhere. Because then one doesn't have to lift the propellant from Earth, but one just lifts the payload and then one gets the propellant from these extraterrestrial sources. And a notable point here is that if this kind of application is realized someday, it means that this is a benefit for all space activities. Although the electric sail directly is only a low thrust method for small payloads, and furthermore, the electric sail cannot be used inside the magnetosphere, of course, because in the magnetosphere there is no solar wind. So we can't use the electric sail directly for making some orbital transfers for satellites. So here is the summary. So solar wind sailing is possible, looks possible and practical, and we have a clear validation path in mind. And then we have there are several applications, but we picked these ones now for study. And then finally, I show you, this is an article which will soon come out in this Swedish popular scientific journal, Allt om vetenskap. So it contains quite nice graphics, not made by me, but by some professional professional artist. Okay, thank you.
Thank you. Time for a quick question.
In order to check this pioneer anomaly, maybe one should not necessarily just head for large distances, but rather address the question of highly non-Keplerian trajectories, because that's the main point. General relativity has been tested in connection with orbits that go in the phi direction, but there is not much of a high accuracy test for radial motion. And so what I would imagine could be useful is to stay on a radial, on a stationary track where you hover, and then you can turn off the electric charge, and then you fall back, for example, and can go back and forth.
Okay. Yeah.
So that way, if you have high accuracy on the spacecraft, that would provide a completely different pathway of testing
Yes, but
relativity accurately.
yes, but I would say that if we are operating the electric cell, I wouldn't dare to say that the accuracy is good. In that case, I mean.
Yeah, but if you turn it off,
yes, then the accuracy is good. Yes, yes. Once we turn it off, except that there is some. I mean, these wires act to some extent as solar cells also. They react to sun's photon flux. So I don't know how accurately this can be modeled, but I mean, yeah, that's one possibility.
Ethan, you have a question?
I actually, it was just a technical question. I didn't quite follow the scaling of the flux. Is it because the Debye length gets bigger as you go out in the solar wind?
Yes, when you move outward, the Debye length actually increases linearly. So at Jupiter distance, the Debye length is 5 times larger as at 1 MU.
Okay, but you have a scaling below 7.6, and that was what we said.
Okay, the 7/6 comes from the consideration that the electron temperature also decreases somewhat. So it goes as the inverse 1/3 power of the distance on average actually. So that's a minor detail actually.
Yeah, please.
In case that eventually this spacecraft is going to cross the termination shocks,
yes.
Is there anything critical in design, or it just crosses the?
No, I mean at that point it's like any other spacecraft. I mean we have already shut down the electric sail at that point. Actually, probably already at Uranus distance.
Yeah,
so I mean, okay. So whether we jettison this system or whether we just fly with the wires, but with no electric field, I don't know. But in either case, it's just like any other spacecraft. I mean, this method just gives it the initial speed, and then it continues with that one. So there is kind of a propulsive phase, and then there is a cruising phase. And this termination shock is well into this cruising phase. I mean that means free flying case.
Then you use wires for plasma diagnostics and maybe for long wavelength radio astronomy.
Yes, that is a very good question. So we have considered this, but the problem with using them as antennas is that their resistance is a bit too large for that. So the resistance of this very long antenna wire is about 1 mega ohm, which is much larger than the free space resistance, which is about 370 ohms. So I'm afraid that it's not an efficient antenna for that reason, unless we find a material which goes superconducting at high distance from the sun. But then additionally, I mean, what might work much better is that one could use them as dust detectors, because I mean, if a dust particle or micrometeor collides with a wire, it generates a small cloud of plasma, which starts to expand, and then it produces an electromagnetic signal which propagates along the charged tether in both directions. So we might be able to sense this electromagnetic pulse, and in that way use it as a very high effective area dust detector actually. So this is one of the double use things that we have been considering.
Okay, thank you very much. Final. Central first.
Too high,
Too high?
I think,
Everything on? Yes.
but it's okay.
Okay, our final speaker this morning is Rainer Art, and he's telling us about magnetic field generation for AP stars.
Thank you very much. Can you hear me well?
Yes.
I think so. So this is kind of an application of dynamos. I'm not seeking for origins or things like origins of turbulent dynamos, things like that. The problem is AP stars. We have heard a couple of things about the Sun, but not much about other stars so far. That's why I would like to introduce you with the characteristics of this type of stars. This is stars which have more mass than the Sun, kind of 2, 3, 4, 5 solar masses, and a fraction of these stars show magnetic fields which are partly very strong. They start from about 300 Gauss and go up to kilogauss, tens of kilogauss actually, on the surface. So these are visible, mostly radial fields on the surface. The lower limit is a real limit. The observational accuracy is so high, meanwhile, that you can actually show that this is not a cutoff by observational effects. So they really separate somehow from normal A stars. A typical thing of these AP stars is that they rotate more slowly than normal A stars. And also in that sense, they form not just a slow tail of the distribution of rotation periods among A stars, they actually show a separate distribution of periods. Normal A stars rotate with 1 day or even less than this, while AP stars have 1 day or more, 10 days, even 100 days, and 1,000 days are known. The longest one is a suspect with, I think, 70 years or something like this. I don't know how accurate that is. So quite strange stars. And the question is, where do these magnetic fields originate from? To find out from where, we need all the characteristics we can measure. And one thing is that these fields, unlike the Sun, they're not aligned with the rotation axis. They have all kind of different inclination angles with the rotation axis. And you see this is plotted here over the rotation period. And the funny thing is that the slower these stars rotate, the smaller, that is, the more aligned these angles get. While when you come from dynamo theory, you will always think if you have the slightest differential rotation, then rotation will make things axisymmetric and make it aligned. So you would expect the small angles at fast rotation and the large angles at slow rotation. That's not the case.
And what does it mean, red and blue spots?
Oh, these are stars of different types of accuracy, which is somehow technical. I should have plotted them in the same color here.
Same, for simple
It
people.
doesn't matter for us now.
Is one of them less accurate?
And the red ones are the good ones.
Ah, okay.
No, it's hard to say.
But I think this is really,
Interesting,
it's a matter of how, I forgot how it was. I forgot. I don't think I would give a precise explanation of the meaning. It doesn't really matter for us now. But the scatter, in fact, the scatter is real. So these are not only observational inaccuracies. It's the characteristics also of these stars that whatever trend they also show always a large scatter of their properties. And the fields can actually be quite complex. This is an example. Usually you would just take a dipole and rotate it. This was done in the graph before, and see which fits best. But actually you can see that these things are not always just dipoles. They may be quite complex. This is the strength of the magnetic field on the surface of such a star at different viewing angles, at different phases. And it was shown that it cannot just be explained by very few spherical harmonics. You need kind of 20 harmonics to fully match this field. And we can also ask how many of A stars are actually peculiar in having magnetic fields. And this fraction increases from the smaller stars to the larger stars. You get more than 10% at the end. Now when asking maybe some more characteristics will come to my mind later. When asking for where these magnetic fields come from, we have a couple of possibilities which I have listed here. one could directly ask for a dynamo, and because these stars have an extended radiative zone. There is no convective shell like in the Sun, so nothing about small-scale things and so happening in there. But still, if you have a meridional flow and perhaps a slight differential rotation, then you can still expect a dynamo, a laminar dynamo. But this dynamo will always deliver regular fields, nicely aligned, m equals 0, m equals 1 mode, something very regular. But we see a strong irregularity in the field. Also, it is quite difficult to excite these dynamos, at least in the numerical range where you can compute. You could also consider a dynamo in the convective core. That 20% of radius is a convective core, and you could think of a dynamo in there. This has been computed in simulations already by Matthew Browning and Sasha Brun. And they do find dynamo action in these cores. They can get up to 100 kilogauss in there, but they don't see how these fields rise to the surface efficiently, that you see 10 kilogauss on the surface. So this gap is not yet filled. It may be some Park instabilities of fields rising up, but then you would expect a variability in these fields. These fields are obviously there's no variability known, so there may be some, but it must be very slow then. The other thing is you could ask for magnetic instabilities in these radiative zones. Maybe there are hidden toroidal fields, for example, which get unstable and produce all kind of irregular outcomes then. But then you need to explain how these strong toroidal fields have ever built up in there without having a dynamo around. And then there's the possibility of the protostellar phase, which is shortly fully convective. During that time, we could again go back to all our knowledge of convective dynamos, plug in alpha effects or even try full simulations and see what happens then. And then, so this is likely to be existing. If you have convection, you will be much more easily believe that there is a dynamo in there. Then the question is, what remains of this initial phase of dynamo for the star in the end? Or, and that's the general assumption for these stars, there's no dynamo at all, no instability at all. These are fossil fields from the formation of the star, which have persisted until now and are showing all kind of geometries now as a result of all kind of geometries during star formation. But the big problem of this is that if there is any smallest convective phase in the beginning, this destructs fields quite efficiently. These convective stars will also be differentially rotating. So the question is, what can remain of any fossil field? I'm concerned with the one but last point. I'm trying to, not really simulate, to make a computation of a mean field dynamo for the convective protostellar phase. This has been done earlier, very early by Manfred Schissler in 1975, with a very, very small grid, finding some dynamo action, of course. Then Leonid Kichatinov was applying that to the Sun for m equals 0 and m equals 1 modes. He wants to see whether there is a remaining field in the core of the Sun, which will add to his explanation of the Takoff line of the Sun. And now we try this with some more massive stars, like these A stars. I had the choice either doing a crude approximation, like the alpha effect, or a crude resolution of a direct numerical simulation. So I chose the mean field dynamo, and I simulate a kind of full sphere. I have to cut out a small hole in the middle because of technical reasons. And I add differential rotation to this. I have an alpha effect in there, which is anisotropic. I will show that later. And I have a magnetic diffusivity, which varies over radius. That is to have a radiative core coming up in the middle. So we have the alpha equation. We have an eta which varies with radius. That also means that if you say that this turbulent eta is coming from a turbulence, then the turbulent gradient will also produce a diamagnetic pumping, which is the last term in here.
And eta, what is it? It's scalar.
Excuse me?
Eta is scalar in your equation? Eta.
Yes, it's a scalar, yes. Right, so I have no anisotropy also in eta. Just in alpha. So the velocity is an angular, kind of solar-like angular velocity profile, which is only present in the convective part of the shell. Just to show you what Leonid and Günther Rüdiger were doing with this diamagnetic pumping. So there's no velocity at all in this computation, so just take an initial field and see how it is pushed into the radiative core of the sun, in that case, to see how much the field can be confined by this pumping in the core of the star. And that works very well. And I included also that term to see the effect in this evolutionary model. So we have an alpha term and an alpha quenching. We put alpha ZZ to 0 for, actually, which is only for fast rotator, but that may be quite suitable for our purposes. These stars have all 1 day rotation period. And so alpha is anisotropic, eta is a scalar. I'm using the code by Rainer Hollerbach, which is a spectral spherical code. And I just use the induction equation for obvious reasons. And this is the evolution I'm plugging in. So while running the code, I'm changing the place where convection is. So the change of the convective zone changes. And after a long time, I also wanted to start with the initial, internal convective core. But computations right now are running up to here. So there was not enough time to get this to that point there. These timings actually are pretty well known from evolution models from stars. I took these from Evelyn Alessian. Which are pretty new models. And then, of course, one could ask, what makes AP stars different from A stars? Why are there so many? Why are there 90% normal stars and only 10% AP stars? So there must be something initially or so which differentiates them. And I tried different inclinations of the initial field. This is this is a 90-degree inclination. The field is a horizontal field threading the star, while here it is an inclined field 45 degrees, which goes through the star. Okay, let's see what comes out. If you put in an A0 mode, the antisymmetric, axisymmetric, antisymmetric mode, and you put in a horizontal mode giving the 45 degrees, then of course you get dynamo action in these. You get dynamo action in the m=1 mode here, symmetric m=1. And these are the only two which come up. The others are essentially 0. The diffusivity contrast in this computation is only 1 to 1,000. You can do more, but then the computations get really more complicated. Not so because, of course, your time step is not, you don't have numerical problems in the interior because of the low diffusivity.
Excuse me, please, in what units mode power?
Oh, well, B is always measured in equipartition B.
But it's fair, you believe that the level of your turbulence is something constant?
Yes.
Mm-hmm.
Yes, and alpha is just there where convection zone is, and it is distributed by cosine theta.
Yeah, I understand, but the question is, what's the profile of turbulence you have got in your calculation, effectively? It's the same as turbulent diffusivity. You've got constant.
Yes. Yes.
Constant
so if you relate it to the RMS velocity, then it's the same. So eta is in the shell is 1, and in the core it is a smaller value, and here it is 10 to the minus 3. The interesting thing is, as you get to thinner and thinner shells, you don't get the m=0 mode starting to dominate. So there's always the m=1 mode which is dominating. Even at the end, when the convection zone completely vanishes, the remaining field, and there the kind of frozen in field, then is an m=1 field. So So that's snapshots in the middle of the computation. So the convection zone has already receded quite a lot to the outer parts. This is a typical picture of omega. This is the distribution of eta, so this makes things more clear now for your questions. And this is how the field is. You see the dynamo mode in here, which is a poloidal field, and much of the field is pushed into the radiative zone, where strong fields can actually pile up during the run. If you run this for a while, then you see the convection zone has essentially vanished here. Most of the eta is now 10 to the minus 3, and the fields in there are m=1 fields which are surviving, while the dynamo in the convection zone is switched off. Field does expel here to the poles. And that's how it looks like on a surface. So in the beginning it's the dynamo mode, m=1, this is nothing really exciting. And then at the end all the surface fields concentrate at the poles. Now we can ask about the actual field strength remaining in a fixed point. This is a fixed point in the core, and that's a fixed point very near the surface at the equator in both cases. And we see that the field in the core always is much stronger than the surface field. Another thing would be if we can pile up enough field in the core, then we could ask for possible instabilities going up there. So then we would have the link to the other option of generating a P-star fields by instabilities. Once we generate enough in there in the radiative core, then we may ask for instabilities, strong field instabilities, like the Taylor instability, for example, which comes from toroidal magnetic fields. But then, as a secondary effect, you get all kind of strange geometries of fields, just because these fields piled up in the middle are strong enough. I do get, at just a few points I took from the computation right now, get to 12B equipartition in B5. That's the maximum ever reached in this simulation, which is quite quickly after the start, after 400,000 years, volume and then decaying. That's a picture of an instability, but a different one. It's a completely different run now. It's the MRI in spheres. Just wanted to show you that you can create relatively complex fields on the surface by an instability internally. But the difference here is, of course, that this is a poloidal field instability, and it's actually a weak field instability, which comes up for weak magnetic fields. Also, the fields produced by the MRI on the surface are of the order of Gauss or 100 Gauss, but they are never 10 kilogauss. Just to show you an example what might be the option of generating complex fields on the surface of AP stars, but probably not with the MRI. Right, then there's some very strange thing about the explanation of the AP stars. What I always find is that when people show their statistics of these stars, there's always a deviation at 3 solar masses. So maybe there are actually 2 groups of stars which need 2 different explanations for their magnetic fields instead of just one. They just look similar. But this is only my impression from all the things I've seen. People always put things like, if they're more than 3 masses, if they're less than 3 masses, then it's like that or that. So this is the thing we should have keep in mind when searching for the explanation of the magnetism of AP stars. Alright, let me summarize that the alpha square omega, which I have plugged in this evolutionary model, changes the topology of the initial field quite strongly. You get dynamo action very easily and very quickly, actually. Much quicker, actually, than I computed here, because my diffusion time was artificially large. So the real dynamo will act even quicker. So the question is, what really of this fossil field, which is usually used to explain AP star magnetism, will survive? If something survives, then it could be the field of an initial dynamo. Of course, I could improve a couple of things. I don't think these things will change much of the computations. It would be more interesting to have meridional flow in there. That could change the results quite considerably. And then, of course, the option should be studied whether the toroidal fields generated in there are capable of showing Taylor instability And that could then be an explanation for the various geometries of AP stars. Best would be direct simulations, of course, but as difficult as they are, I don't believe they will be available quickly. Okay, thanks.
So these stars live for a long time.
100 million years.
Right. So your simulation is just carrying out the first
Exactly.
stages.
Yes.
What can the magnetic fields of white dwarfs tell you about the long-term field stability or strength of these stars?
They could tell something. Yeah, I've no real data now in my head.
Don't they also show like there's a small population of high field white dwarfs which are separate from the main body?
There is something like this, but it's very vague, I think. I'm not sure now about the detailed results. Sorry, but we can look it up.
Let me ask a question in general, in some sense, about stellar hydrodynamics. I understand that IP stars normally have convective core.
Have what?
Convective core.
Convective core.
But if you've got in this core, of course, differential rotation.
Yes.
My question is why in the so-called radiative zone, if you've got differential rotation, you have some kind of turbulence? It's a general question. If you've got differential rotation, you've got shear. If we know from our experience in Earth, for example, that in Earth's atmosphere we've got shear. It's enough not to produce turbulence. Today we know how to organize turbulence in presence of stable certification. Maybe it's a good idea a little bit to discuss all this point of view, that we have any turbulence in radiation zone.
Yes. That's actually a little bit is visible in these computations by Browning and Broom, because they have also more than the convective core, and they see how differential rotation spreads out of the core a little bit, and they could have the chance to see something like this.
Discuss how we can model in view of these ideas.
Yeah, well, I assume that it is there in the radiative zone, of course, but who knows?
So it's next step.
In the beginning you showed some picture, was it observations or some simulated star?
This one?
Yeah, maybe.
This was observations. Doppler Zeeman imaging.
Kotchukov.
Yes.